Good afternoon, class. We are looking at chapter 4, exponential and logarithmic functions. And here's 4.5 logarithmic properties, section 4.5 logarithmic properties. We have covered the exponential functions, graphs of exponential functions, logarithmic functions, graphs of logarithmic functions, and now logarithmic properties. So the objectives are use the product rule for logarithms, use the quotient rule, use the power rule for logs, expand logarithmic expressions, condense logarithmic expressions, use the change of base formula for logs. So here's the exponential functions. As you know, when a is f of x equals a to the power of x, when a is larger than 0 and a is not equal to 1, it represents an exponential function. When a is larger than 1 is an exponential growth. Between 0 and a, it's an exponential decay. When it's 1, it is not an exponential function. It's a horizontal line. What do they have in common? Horizontal asymptote is the x-axis or y equal to 0. Vertical asymptote, we don't have any. Y-intercept is 0, 1. X-intercept, we don't have any. Domain, all real numbers, range from 0 to infinity. They are identical. However, in the case of a larger than 1, we are dealing with an increasing function. It's an exponential growth, which means the limit of f of x as x approaches infinity is infinity. The first quadrant, x goes to infinity, so does y. However, the limit of f of x as x approaches to negative infinity is 0, and that gives rise to this the definition of a horizontal asymptote, which is the x-axis or y equal to 0. When a is between 0 and 1, in this case, it's a decreasing function, which makes it an exponential decay, in which case limit of f of x as x approaches infinity is 0, as x goes to infinity, y goes to 0. And that's again the definition of a horizontal asymptote. The limit of f of x as x approaches negative infinity is infinity. That means the second quadrant. Logarithmic functions and graphs, remember when we want to go from one format to the next, to convert from exponential form to logarithmic form, x is b to the power of y is log x to the base b. They both have the same exponent, namely y, the name base, namely b. And this is the result for the exponential. This is called the argument of log. And the relationship between logs and exponential functions is such that they are inverse functions. With respect to y equals axis, they become symmetric. For example, y equals ln x and y equals e to the power of x. If you have a common log, that means the base is 10, and you use log, and you don't write the base. And y equals log x, and y equals 10 to the power of x are inverse functions. And so it comes from the fact that if you have log x base b equals y, with this arrow, we can write the equivalent exponential format of b to the power of y equals x. And from here, we can see it for a natural log, y equals ln x, means x equals e to the power of y. For common log, y equals log x equals 10 to the power of y, when x is, of course, larger than 0. The argument of log is always positive, everybody. So for x larger than 0 and a larger than 0 and a is not equal to 1, the expression log x base a is read the logarithm of x to the base a, or simply log base a of x. That's how you would read that. Let's look at some logarithmic properties, knowing the fact that was mentioned here with this arrow. B to the power of y equals x. So in the case of a general log, where y equals log x base b, and therefore b to the power of y equals x, we have the following properties. I have given them numbers so we can compare and contrast with other logs of different bases that are known to us, such as natural log and common log. So for example, we want to make sure we understand the first one. Log 1 with any base, b is 0. If you look at this arrow, you can see b to the power of 0 is 1. The second one indicates log b base b equals 1. If the argument and the base are identical, the answer is 1. Again, if you go with the arrow, you see that. Log base b of b to the power of x is x. If you go with the arrow, b to the power of x becomes b to the power of x. B to the power of log x base b equals to x, which means if you raise b to the power of log, where that log has the same base as this one, the argument will take over. Numbers 3 and 4 refer to the fact that logarithmic functions and exponential functions, they are inverse functions. Number 5, log x y base b is log x base b plus log y base b, which means we are using the product rule. Sometimes we go from right to left, sometimes we go from left to right. Log of base b of x over y, known as the quotient rule, is log x base b minus log y base b. And finally, the power rule. This is called the quotient rule. This is the power rule. Log base b of x to the power of n equals n log x base b. So the exponent becomes the coefficient. Let's go to common law. When we write y equals log x, that means the base is 10. And therefore, we don't write it. So 10 to the power of y equals x is the equivalent exponential form. So if we want to write this for common law, notice what happens. The first one, you don't have to write the base. The second one, because when we don't write the base is 10, this must be 10. And the same thing here, because we don't write the base must be 10. So 10 to the power of x. And with that goes number 4. The base is 10. 5, 6, 7 are the same as 5, 6, 7. Do not write the base b. So basically, drop the base b. 5, 6, 7. If you drop the base b, you're dealing with common law. In the case of a natural log, y equals ln x. That means log x base e. Don't write this. Always write this, okay? So the exponential format would be e to the power of y equals x. So if I want to write number 1, I would just simply put ln 1 equals 0. If I want to do number 2, instead of log b, I have to write ln. The moment I put ln, the base is e. So I have to write ln e equals 1. The third one says log base b of b to the power of x, because when we write ln, that means e, so it must be ln of e to the power of x, which is x. This one, the base is e, so e to the power of ln x equals x. Take a look at the first 4, as I mentioned. And then 5, 6, 7, just instead of log, in fact, it's easier to go here. Instead of log, just write ln. It's the product rule, the quotient rule, the power rule. Again, the graph indicates logarithmic functions and exponential functions are inverse functions, therefore symmetric with respect to the line y equals x. It's the change of base formula. I want you to pay attention to this. Log x base b is log x over log b with any base of your choosing, for example, base a. However, we choose either base 10, common log, or base e natural log because those are the ones basically that the graphic algorithms can handle. Ln x is less than 0 for x being between 0 and 1. So if you look at this, the domain is from 0 to infinity. If it's in this vicinity, this portion is below the x-axis. And ln x is 0 at 1. So let's look at this one and say this point. Let's look at this point, this part, and means this portion. And this part means this portion of the graph. When ln x is positive, larger than 0, x must be larger than 1. There's one more interesting thing, okay? Because the curve y equals e to the power of x crosses the y-axis with a slope of 1, so that means over here, okay, that it follows that the reflected curve y equals ln x crosses the x-axis with a slope of 1. This is the concept that is useful for calculus. In other words, over here, if you were to draw a tangent line, the slope would be 1, the same thing here. Let's see if I can do an okay job on that. So these two lines are parallel with the same slope. Those are the tangent lines. Let's look at quickly some of the proofs. So we have the general log rules here. And we are saying log x y base b is log x base b plus log y base b, and log x over y base b is log x base b minus log y base b. So those are numbers 5 and 6, for example. 1, you don't have to just b to the power of 0, 2, b to the power of 1 is b, 1 and 2 are basically, proved in no time. But let's see how that thing works, and you can find them with more details at the end of the lecture. So what we are going to do, we are going to define log x base b as something, for example, m. And therefore, by definition of an exponential, b to the power of m must represent x. And log base b of y, we are going to represent it with something other than m. You can't use the same thing now. Let's say n, in which case b to the power of n equals y. So on the left-hand side, we have log x y base b, and so we are going to replace the x and y accordingly. X is b to the power of m, y is b to the power of n, and according to the exponential rule, we can write this as b to the power of m plus n. So log base b of b to the power of m plus n. Number 3 says this is x. Therefore, this must be m plus n. And now m, replace it with log x base b. N replace it with log y base b, and that's the end of the proof, everybody. This proves number 5, known as the product rule. What about this one? We start with the left-hand side and we ignore the right-hand side. And we replace the x just like here with b to the power of m, and y just like here b to the power of n. So here's the left-hand side. Log base b of x, which is b to the power of m, over y, which is b to the power of n. Using the exponential rule, this becomes log base b of b to the power of m minus n. And the third rule, again, the third rule class, by the way, just look at the arrow. There's really not much to prove. So the answer is m minus n. And again, instead of m, we're going to put log x base b. Instead of n, we're going to say log y base b. And that's the proof. Let's look at number 7. Rule number 7, the power rule says log base b of x to the power of n is n log x base b. So how do we prove that? We are going to start with the left-hand side again. And we're going to say log base b of x to the power of n. We are going to replace the x here. What do we have? B to the power of n. So that means b to the power of m to the power of n. This doesn't go away. And by the power rule, this becomes log base b of b to the power of m times n. And again, according to the third one, the answer is the exponent because the base and the argument are the same. Capital M times n, which is the same as lowercase n times m. That is the commutative property of multiplication. So n times m, n times log x base b, and believe it or not, that's the proof, everybody. So it proved quite a bit. Again, number 1 is straightforward, and 2, and we just proved basically the rest of it. All right. Now that we have proved the properties, we're going to use them. These properties are extremely important, and you have to know them to be comfortable with upcoming courses. So, log base pi of pi cubed. We are looking at the third rule. The answer is just 3. Five to the power of log base 5 of square root of 3. So take a look at the property that we can use here. Take a look at number 4, everybody. Number 4 says, if the base here and here are the same, the answer is this. If you look at this, says b to the power of log x base b is x. So 5 to the power of log base 5 up, whatever this is, the answer is that one, square root of 3. Part C. ln of e to the power of 0.35t. Look at number 3. What would that be for a natural log? For natural log would be ln of e to the power of x is x. I hope you can see that. Therefore, the answer is 0.35t. So recognition of the properties from general log is important. Log base 2 of 4 cubed. We can put the 3 in front. Log base 3 of x squared, we can put the 2 in front. Now, one thing I want to tell you, some of you may recognize this one as 2, and the answer becomes 6 because log base 2. Number 4 is 2 squared, which makes it 2. Okay. But that wasn't the point of this question. Now, 3 to the power of log 7 base 3, 5 to the power of log x base 5. What are we looking at? Property number 4. I was going to say question number 4. Property number 4, everybody. Makes this one 7, makes this one x. Log base 6 of 6 to the power of 5, log base 9 of 9 to the power of x. Look at number 3. It says log base b of b to the power of x is x. So because this is base 6 and this is base 6, the answer is 5. Because this is base 9, this is base 9, the answer is x. So 5 and x. Use logarithmic properties to expand. A lot of these expansions can be done in one shot with enough practice, but we're going to take the time to make sure we get enough practice to be able to handle them in a long run. So first and foremost, we want to decompose. When they say expand, decompose, which means the first thing first, log of the top minus log of the bottom. That is using number 6, the quotient rule. Now each one uses number 7, the power rule. That means 4 sits in front here, becomes 4 log base 6 of x. 2 sits in front, becomes minus log base 6 of x squared plus 3. And we're done. Part B, log base 2 of x squared times cube root of square root of x minus 1, x is larger than 1. And so we use number 5, the product rule, because it's the product of x squared and cube root. So log base 2 of x squared plus log base 2 of the cube root. So that is using number 5, the product rule, everybody. Now, before we go to the power rule, let's change this to x minus 1 to the power of 1/3. So we change this expression to x minus 1 to the power of 1/3. And now for both cases, we use number 7, the power rule. 2 sits in front here. 1/3 sits in front here, according to property number 7, called the power rule. So this is 2 log x base 2. This is 1/3 log of x minus 1 base 2. And we're done with A and B. ln of x cubed square root of x minus 2 over x times x plus 1 quantity squared. X is larger than 2, and we want to decompose this completely. First and foremost, we use number 6, the quotient rule. So the log of the top minus log of the bottom. In this case, the ln of the top minus ln of the bottom. So ln of x cubed square root of x minus 2 minus ln of x times x plus 1 quantity squared. So that's the first step. Now the second step, we are going to decompose it further as follows. This one uses number 5, the product rule. Ln of x cubed plus ln of the square root. Minus, now we're going to use again number 5 on this one, minus in brackets ln of x plus ln of x plus 1 squared. Pay attention to the following. So ln of x cubed plus ln of square root of x minus 2. I've seen students sometimes making a mistake of writing minus ln x and then plus ln of x plus 1 quantity squared is wrong. Make sure this whole thing goes into the brackets if you have a negative sign, because it will change everything. However, if it's a plus sign, then it doesn't matter. So let's see what happens next. We're going to use the power rule. Before we do that, this guy, we are going to write it as x minus 2 to the power of 1/2. Now, very carefully, ln of x cubed becomes 3 ln x. So this one 3 sits in front. Ln of x minus 2 power 1/2, we put the 1/2 in front. We're done with that. Minus ln x. And before we apply that, we are going to put the 2 in front. So again, 3 ln x plus 1/2 ln of x minus 2 minus ln x minus a 2 ln of x plus 1. And that's the final answer, everybody. Everything is about knowing the properties and knowing how to decompose this. This does take a little bit of a time, but when you get comfortable with the properties, then not only this becomes easy, but also later topics that depend on logs. Now the reverse process, write the expression as a single log. Now we want to put them back together. Again, you can do it in one shot or in several steps. Ultimately, with enough practice, you can cut the number of steps. So this one, remember, we want to put it into a single log, and that's the key. So ln of 2 cubed here, the second one, don't change it. And then ln of 2 cubed, of course, that means 8, right? So what did we use here? We used number 7. Now, what do we use? Number 5, and by the way, we want to go this way, okay? Product rule. This was a power rule. We are going this way. So therefore, ln of this times that ln of 8x squared. And we're done. Single log. What about this one? First, we use the power rule number 7. One half becomes the exponent for 4. 2 becomes the exponent for 5. That is the reverse process of number 7, going this way, everybody. And we know this is 2. We know this is 25. So log base A of 2 minus log base A of 25. We are going to use number 6. The quotient rule, and we're going to go from right to left. So log base A of 2 over 25. That's the final answer. Part C, negative 2 log base A of 3 plus 3 log base A of 2 minus log base A of x squared plus 1. Pay attention to the base. You can only combine them when they have the same base. So we are going to go with the power rule and the reverse process. So negative 2 becomes the exponent for 3. Positive 3 becomes the exponent for 2. So this becomes log base A of 3 to the power of negative 2 plus log base A of 2 cubed. The third one doesn't change. Again, you can do it in one more shot, but let's do it in 2 shots. Because there's a plus sign, you can combine this using number 5, the product rule. Again, you're going from right to left. So log base A of the product of these 2. We are not changing this one. As you know, this is 1 over 9. This is 8. So it's log base A of 8 over 9 over x squared plus 1. So 8 over 9 over x squared plus 1 looks like 8 over 9 times x squared plus 1. I hope you see that this is 8 over 9, so the 9 belongs to the denominator. The other method that you could use, if you just put the 2 here, you get 9 and combine these 2 into 1 and put it at the bottom. Either way makes no difference. As long as you know how to use the properties, you can use them in any order and how you want. It's absolutely up to you. Change of base formula, evaluate logs whose base is neither 10 nor e. So log x base e, we said, can be log x over log b with any base a. And therefore we choose common log, log x over log b, or we choose natural log ln x over ln b. So let's quickly look at the proof. As you recall, we said log x base b, let's say it's m, so b to the power of m is x, log base ab to the power of m. So we just stick with that. So log a of b to the power, and if I take the log of this expression now, both sides with respect to a, so this one becomes log base a of b to the power of m, this becomes log base a of x. So take a log of both sides. And observe, see what happens. This one, according to the power rule, I can put the m in front, and therefore m is the right side divided by log base a of b. In other words, if I divide both sides by this log base a of b, I get m. And what was m? Log x base b. Log x base b is log x base a over log b base a. So that's the proof for the change of base formula. Very straightforward, everybody. Very straightforward. But it has, a lot of applications, especially when we are dealing with logs that they are not natural log or common log. For example, log base 5 of 89. We have two choices. We can say log 89 over log 5. That means we choose base 10. We can say ln 89 over ln 5. That means we are choosing the natural log. And we are not saying log 89 equals to ln 89. We are saying this ratio is equal to this ratio using a calculator with a bunch of decimals. How many decimals? Whatever they ask you. If they don't, minimum you want to go with 4 or 5, okay? And there you have it. It's very straightforward. You just use a calculator, but you have to know what to do first. All right. How about this one? We can use either natural log or common log of square root of 5 over square root of 2. So log square root of 5 over log square root of 2, or ln of square root of 5 over ln of square root of 2. Now, you can put it to a calculator just the way it is. Okay. However, you could also say this is 5 to the power of 1/2. This is 2 to the power of 1/2. Take the 1/2 in front according to the power rule, and you can get rid of this 1/2. But you have two choices: log 5 over log 2 or ln 5 over ln 2. The 1/2 cancel each other, okay? And you end up with, again, bunch of decimals at this point using a calculator, 2.3219. Again, because you were using a calculator in the first place, everybody, it wouldn't make any difference if you just put it just the way it is, like this, instead of continuing with that 1/2 that I mentioned in a calculator. It makes no difference, but I just wanted to show you that. All right, right, in terms of A, B, and C, ln 2 is A, ln 3 is B, ln 5 is C. Let's do that. The first one is given ln of 6 over 5. All you have to do, write everything as factor of 2, 3, and 5. So this is fine. The numerator, you write it 2 times 3. And now combining 5 and 6, everybody. Combining 5 and 6. By now we can do that. This is ln 2 plus ln 3 minus ln 5. So A plus B minus C. A cube root of square root of 25. First and foremost, this is 5 squared. And so you have ln of 5 to the power of 2/3. All I'm doing is doing exponential rules, going from root format to exponential format. And now using number seven, I'm going to put 2/3 in front and replace the ln5 with c 2/3 c. We are done. Number 24, you may know it's 2 cubed times 3, or you may not. If you don't, you do the factoring. Number 24, if you divide it by 2, you get 12. 2, you get 6, you get 2, you get 3, 3, you get 1. And this is 2 cubed times 3. So that means ln of 2 cubed. Maybe I write that just because we want to get enough practice. So this is ln of 2 cubed plus ln of 3. So 3 ln 2 plus ln 3, right? Because 3 becomes the coefficient. Number 7, 3 ln 2 is 3a, ln 3 is b. 3a plus b is the final answer, everybody. Decompose the log ln of 2x squared of x squared plus 1 over x plus 3. First, we do it in a couple of steps using number 5. We are going to write ln of the top. My apologies, number 6, the quotient rule. Ln of the top, which means ln of 2x times squared of x squared plus 1, minus ln of the bottom, which is ln of x plus 3. That's the first thing. Then we are going to separate things. Let's see if we can do it in one shot. First and foremost, this changes. X squared plus 1 to the power of 1/2. Now, let's see if we can do this in one simple shot. This guy doesn't change. Oh, this guy doesn't change. This one is ln of 2 plus ln of x plus ln of this one. And this one is x squared. I should actually write this at top of it first. This is x squared plus 1 to the power of 1/2. So that's important to know. All right. So ln 2, ln x, and ln of this part 1/2 sits in front. This one, log of the top minus log of the bottom, we are looking at the quotient rule. Now, normally we would be done. However, we know that this is the product of x minus 2 and x plus 2. That's why we are not done, because we're going to completely decompose this. So this is log base 2 of x minus 2 plus log base 2 of x plus 2. The third piece doesn't change. This had a long animation. It should have showed up first. Anyways, use log properties to expand. Decompose means the same thing. And again, we are familiar with all of these properties. Obviously, we are going to use Number 6, the quotient rule, log of the top minus log of the bottom with the same base. So log 29 base 8 minus log 43 base 8. What happens here, we are going to use the product rule. Product rule, number 5. So log 5 base 4 plus log 180 base 4. Part C, we are going to use number 7, the power rule. The exponent becomes the coefficient, so 1/5 sits in front. 1/5 log base 10 of 22. Now, normally we don't write the base 10. This is given in this format. We give it back in that format. But log, when the base is 10, it shouldn't be there, okay? Log base 7 of 7 over 9, and we use number 6, the quotient rule. Log of the top minus log of the bottom with the same base. So log 7 base 7 minus log 9 base 7. Normally we would be done, but this one, we should recognize this one as what? 1. Log 7 base 7, number 2. This is number 2, property number 2. So that's why we must check it. We must change it. Okay, everybody? But here, let's work out those expressions. This one is following number 5, the product rule. Log x base b plus log x plus 5 base b. It's important to keep x plus 5 in the parentheses. If you don't have a parentheses, it has a different meaning. Log of PQR, just separate them into 3 pieces. Again, using number 5, the product rule. Log P plus log Q plus log R, no base, means base 10, means common log. Log base 3 of x over x minus 9, we are going to use number 6, log of the top minus log of the bottom. So log x base 3 minus log x minus 9 base 3. And again, you have to be careful and keep this in the parentheses, or it has a different meaning, everybody. It has a different meaning. Write the expression as a single log, log base 4 of 7, log base 4 of 4. That means, again, you are going to use number 5, but you're going to go from right to left. So log base 4 of what? 7 times 4. And 7 times 4 obviously is 28. So log base 4 of 28. Log base 3 of 4 plus log base 3 of x plus log base 3 of 2x minus 5. So you have to put them all together. So using the product rule and going from right to left, we're going to write log base 3 of 4 times x times 2x minus 5. 4 times x times 2x minus 5. Now, first and foremost, I didn't put a bracket on purpose here, but really it's a good idea to have a bracket, meaning the whole thing represents the argument of log. Secondly, it's a good practice to distribute. When you do that, 4x times 2x gives you 8x squared. 4x minus 5 gives you negative 20x. So the final answer would look like this: log base 3 of 8x squared minus 20x, because we are distributing. Log base 6 of 108 minus log base 6 of x, and we use number 6, the quotient rule, and we're going to go from right to left. So log base 6 of 108 over x, and it doesn't simplify any further, because if this expression, we can combine them and simplify them, we must, as we did here. 7 times 4 is 28, we must. Log base 5 of x minus log base 5 of x squared plus 6. And again, we are using number 6, the quotient rule, and we're going to go from right to left. And we're going to write log base 5 of x over x squared plus 6. So this becomes the top, this becomes the bottom, and it can't be simplified. Since it can't be simplified, that's the final answer, everybody.